So 7-3 is simplifying
Looking at it.
and add, subtract. So we created this kind of a new number system with these radicals, kind of like when you learned whole numbers, you learned how to add them, subtract them, multiply and divide them. You learned fractions, you learned how to add and subtract, multiply and divide them. You learned decimals and you did all 4 operations. So we learned this new thing called radicals. And they're, for the most part, they turn into irrational numbers if they don't break down. So we have to learn how to add, subtract, multiply, and divide irrational numbers. Do you remember what irrational numbers are from like the first day of class? They're numbers that cannot be written as something over something. Square root of 2, pi, square root of 3, cube roots of 5, weird things like that will turn into irrational numbers. They're decimals that never terminate and never ever repeat, technically. They're one of the weirder numbers to try to understand. Nice coat. Still a poor bunny around your neck. So, you can't. Bunnies are cheap. So let's start off with something easy. There's 2 ways of looking at this. We can look at it the book way, or we can look at it my way. Now, the book way is really good for small numbers, but it doesn't work really well with larger numbers underneath a square root or a cube root. So I want to show you both methods, and then you can choose which one works better for you.
That'd be the square root of 6 times 3.
But I have to get into a rule first. So, rule number 1 with radicals. I'm going to build the rules up with examples like last time, so you can kind of see why I'm needing these rules. The square root of a times the square root of b is equal to the square root of ab. But this rule can be written in 2 different directions. You can write it as a combination of radicals, or you can take it and use it as a breakup of radicals. So the way we're going to use this rule is we're going to take this product, square root of AB, and separate it into the square root of the first one times the square root of the second one. No, this does not work over addition and or subtraction. It only works between multiplication and division. You'll see a little bit later. One condition, especially if it's square roots, A has to be positive and B has to be positive. When you write greater than 0, you just read it as is positive, because the only numbers greater than 0 are positive. Put equals here because it is possible for them to be equal to 0, but that would be kind of pointless, right? If they were equal to 0. Because if one of them is 0, the whole thing is equal to 0, but it's possible you could have it. So this is rule number 1, and this is the way the book does all of their problems. They just use this one rule, and they break it apart into 2 square roots. The problem with this rule is you have to figure out what is the perfect square in 18. So if you break it up into 6 and 3, it's not a perfect square, neither of them. You cannot take the square root of 6 and you cannot take the square root of 3. So you have to figure out what number in here is a perfect square. And that's the hard part. If you look at 18, it's 9 and 2. And that's why I don't like their method, is because you have to know your multiplication facts of squares. So you have to know 2 squared, 3 squared, 4 squared, 5 squared, all the way up to 17 squared. And how many people know that? Not me. I know up to 15, and that's about it. So this rule is great for small numbers, but once the numbers start getting a little bit bigger, it gets really hard to work with. So I'm going to show you their way, and then I'm going to show you my way. So they say, oh, let's break it up into the product of 9 and 2. Because I know 9 is a perfect square root. Okay? And then use the rule, and it splits it up into the square root of 9 times the square root of 2. Okay, that's great. And I know the square root of 9 is 3. So the square root of 18 has to be written as the 3 square roots of 2. You cannot leave the square root of 18 on a piece of paper. That's your final answer. It's like leaving 5/10. It has to be reduced. So this is what's called a radical reduction. So rule number 2 cannot leave a perfect root under a radical, you have to break it down. The most common radical to leave under a square root is the square root of 8. Square root of 8, right? So if you have the square root of 8, what's it break down into by their way? 4 and 2, so you break it down into the square root of 4 times 2. And then this breaks down into the square root of 4 times the square root of 2. And square root of 4 is 2. So you get 2 square roots of 2. So this one, I would highly suggest you just memorize. The square root of 8 is 2 square roots of 2, and you're done. But you can break it down. All right. So let's do one my way. Let's start off with square root of 18 again. Now my way, you don't have to know what the perfect square is. Because most of the time you're going to look at a number and not know what the perfect square is rather than actually knowing it. This is the way I work it. 1. This is really the only thing about my method. Divide by the smallest number possible. That's the only thing you have to do with my rule. So what is the smallest possible number that divides into 18? Besides 1. 1's boring. 2. So what we're going to do is what's called prime factorization. So 2 goes into 18 how many times? 9. And then 9 can be broken up by the smallest number. 2 doesn't go into it anymore, so you move up to 3, and 3 times 3. Now my method kind of goes back to the definition of square root, what we were doing on Wednesday. So if we have something like this, the square root of 2 all squared, what's it equal? It's just 2, right? Oh, let's go over this again. The 4th root of 5 to the 4th. What is it? 5. The 7th root of 11 to the 7th. 11.
The 7's cancel out.
Because the 7's cancel out. One's a 1/7 power, the other one is a 7 power. When they multiply together, you get a single power. So it's 11 to the 1st, which is equal to 11.
I thought you divide.
Well, I did. This becomes 11 to the 7th raised to the 1/7 power. And you multiply power to a power, you multiply. These are multiplicative inverses.
Oh, that's what you're saying.
And multiplicative inverses equal 1, so you get 11 to the 1st power, which is 11. So they kind of just cancel. Just be careful. This one equals what? I'm sad. Thank you.
I know.
I got the 3 fingers from the back of the room.
3.
It's 3.
3.
Why do the square roots have to be
1/2? They cancel out.
positive? It's an even number. It has to be positive.
Oh, yeah.
Okay. So here is actually 3 squared. So if I can find a pair of them, I can take it out as a single factor of 3. So this becomes 3 square roots of what was left behind? The 2 here. Why am I not looking at the 9? I broke it down. So anything that has branches underneath it, you can ignore it. So basically the way my method works, you're going to be looking at this diagonal of factors. So you get 3 square roots of 2, which gives you the same answer. It's just this one you have to know the perfect square, and my method you don't have to. All you're going to do is break it down into what's called prime factors, group 2 of them together, and pull it out. You don't even have to know what it is. So that's my method.
Question.
Go for it.
Couldn't you do like a ladder? You know, like people say you can do it like a ladder, upside down ladder, and have all the prime numbers that go into it on the side, and then like count them up and then find out what's left.
Probably the same thing as mine. I just designed it a little different. If you can look at a number and know every prime number that's inside of it, good for you. But I can't. I need my little factor tree to break it down into smaller and smaller pieces. Especially when the numbers get big. This one's not huge. This is number 10. This one has a little bit of a variable in it. So this is the square root of 16x to the 5th. Now this one we might want to think as a rational exponent. It actually works out better with the variable part. The number part is real easy. So I'm going to do this with their rule, and then we'll find easier ways to do it. Their rule says break it up, so surge 16 times the square root of x to the 5th. Okay. Square root of 16 obviously is?
2.
No. Well, we don't have square root of 16.
Oh,
Oh, it's 4. Don't break down ones you already know.
okay.
So this is 4. I highly suggest you write x to the 5th raised to the 1/2 power. Now, the only reason, this would be like a mental step for me. I wouldn't write this one down, but it's what's really going on. So, when you say 5 times 1/2, you're taking 5 and dividing it by 2. So, 2 goes into 5 how many times? 2 times. Now, that means you're taking 2 factors of x outside. And what's the remainder? 1. So you leave 1 factor of x behind. You want to think about it. X to the 5th factor multiplies out to be x times x times x times x times x. And if I do it by my grouping method, I can group these 2 and bring out a single factor of x. And I can group these 2 and bring out a single factor of x. You learned division this way, where you grouped them and said there's one answer, there's another answer, there's a third answer, my answer is 3. So here I'm going to pull out 2 factors of x. So when I get down to it, it's going to be 4. I'm going to pull out 2 factors of x. How do I write 2 factors of x? X squared. And then you're going to leave behind the square root of the remainder, the guy that gets left behind. So 2 goes into 5 twice with a remainder of 1. Once you get used to it, it's not that bad. It's just you do have to practice it a little bit, get used to what goes in and what goes out. I've had people do it backwards on the test before. I've had answers x times the square root of 4x squared because they get confused between what goes in and what goes out, so be careful with that. I gotta have something harder. Where's number 12? Let's do it my way for the fun of it. Number 12. The square root of 45 a cubed b to the 8th. And we're going to do it my method because I just want you to get used to it. It's one that'll guarantee get you the right answer every time. First thing off, what is the smallest number that divides into 45? 3. So 3 goes into 45 how many times? 15. And then 15 breaks down into 3 and 5. Now this is a square root, so we're looking for a couple, a pair. So the pair is 2 3s. So one thing that's coming out is guaranteed to be 3. All right, so we might as well write that down, 3. When you get to the a cubed and the b to the 8th, just remember that the index is 2. We're going to divide by 2 because it's literally a half power. So 3 divided by 2 is? How many times does it go in? Once. So we're going to get a factor of a on the outside. 2 goes into 8 how many times? 4 times. So we're going to get 4 factors of b on the outside. And then we start worrying about what's left behind. So square root of, what's left behind in the number? At 5. Now, when I went 2 goes into 3 once, was there a remainder? An a. When 2 went into 8 4 times, was there a remainder? No, so I leave it empty. Don't even put b in there at all. If anything, b to the 0, but that's just 1 anyways. So there's your answer. See? Easy. They don't have much harder than that.
So you divide by 2 and 2?
For a square root. Yeah. We'll wait until we get to cube roots. Then what do we divide by?
3.
3. And 4 through 4 and so forth. So the pattern stays the same. The number might change. Number 14. Probably the worst one. Yeah, it's not that bad. 14. The square root of 24 x y to the 8th z to the 3rd. If you do enough of these, you can look at it and know exactly what the answer is, but you have to do a ton of them. So, what's the smallest number that goes into 24? 2. So 2 and 12. What's the smallest number that goes into 12? 2 and 6. Smallest number that goes into 6? 2 and 3. Now, is there any pairs? Pair of 2s. Now, don't group all 3 of them. You just want a pair of them. So we take this pair and we're going to pull it out. So the first part of our answer is going to be 2. Now, work with the variables. This index of 2, which is normally not written, but you might want to write it in there. 2 goes into 1 how many times? It doesn't. So that x is going to be left behind. 2 goes into 8 how many times? 4. So we're going to get y to the 4. 2 goes into 3 how many times? 1. So we're going to get a factor of z on the outside. And then the square root of what's left behind? The 6 from here, 2 times 3, so 6. A factor of x was left behind? Was y left behind? No, so that's all gone out. And then 1 factor of z, because 2 goes into 3 once with a remainder of 1. And there's your answer. I think it's much more efficient than breaking it apart into 2 pieces, simplifying 1 piece, and oh my God. All right, let's increase the index. Now that was boring. That was pretty good. 18. This is the cube root of 128. And like I said, a lot of people, the way the book teaches it is, you need to look at this number and know what the perfect cube number is in here. Now, you all demonstrated that you have no idea what 4 cubed is and 5 cubed is, so my method is going to save you on this rather than doing it the book way. So, what is the smallest number that divides evenly into 128? 2. So you start off with 2. How many times does 2 go into 128? 64. How many times does 2 go into 64? 32. 2 go into 32? 16. Oh my gosh, look at all these 2s. 2 goes into 16? 8. 2 goes into 8? 4. 2 goes into 4? 2. It's all 2s. So 128 is just a product of a bunch of 2s. Now, this is a cube root. So what am I going to group? 3 of them. I need 3 factors on the inside to come out as a single factor on the outside. So I'm going to pull out 1, 2, but there's another group of 3 here. So I'm going to pull out 2 2s. 2, 2. So if I pull out 2 factors of 2, that's better known as 4. 2 squares, yeah, but you might as well just simplify it. It's 4. Then we can, oh, there's no concentration on variables. There's no variables on this one. What's left on the inside? 2. Is this answer correct? Yeah, you better put that cube thing. The square root of 2 is different than the cube root. So whatever the index starts with, you have to make sure the index.
Where you get that 2 on the inside there?
Him. This guy, he's all by himself. If you don't get grouped, you stay behind. You know, all your friends left you and you get left behind. Sad.
No, that's the strongest person.
What's that?
That's the strongest person.
Oh, is it? The one that gets left behind. How about... that one's boring. That one's not too bad. 24. The cube root of 40 x to the 7th y to the 26th. Horrible. You're going to find that variables are much more friendly here than the numbers. The numbers take a little bit more work. The variables are kind of quick. Usually it's the other way around, but in this case, numbers are the harder part. So, 40. Well, start off with the smallest number that goes into it. 2. And 20. And 2 goes into that. And 2 goes into that. Huh? Oh, 2 and 5. I thought you said 25. 2 and 5. Okay. So you get a nice little factor tree. So if you want to think of it as the product of prime numbers, it's 2 times 2 times 2 times 5, better known as 2 cubed times 5. All right, this is index is 3. So we're looking for a group of 3. So here's a group of 3, and we're going to pull it out, and that's going to give us, on the outside, a 2. And then we can concentrate on the variables. With square roots, we're dividing by 2. With a cube root, we're going to divide by the index, which is 3. 3 goes into 7 how many times? 2 times. So I'm going to pull out 2 factors of x. And then 3 goes into 26 how many times? 8. What were you thinking? 3 times 8 is 24. So we're going to get y to the 8. And then left behind, we're going to have a 5. And let's see, 3 went into 7 twice with a remainder of 1. And then when 3 went into 26, it left behind 2. So we get y squared. Is this answer correct? No. I need that 3. I'm just trying to get you to think that if you leave this alone, it's actually the wrong answer. You do need that little 3 in there. Try not to get it too close to that 8, because then it'll look like y to the 83rd. Try to get it in this crook so it's distinguished away from the exponents. And that's your answer. Simple as that. Try doing one the book method and then do it my way, and you're going to lean my way every time almost. Do they get worse? Ooh, there's one. Number 28. Well, this is a horrible one. Let's give myself a little corner over here. 28. The fifth root of negative 243, x to the 4th, y to the 10th. Anybody know the fifth root of 243? I don't know either. Not off the top of my head. Unless you use a calculator and cheat. What is it? Yeah. So, does 2 go into 243? No. So you go up to the next number, which is 3. So, does 3 go into 243? Do you know the trick for dividing by 3? If a number is divisible by 3? If you add up the digits and it's divisible by 3, the number is also. So 2 plus 4 is? 6 plus 3 is? And 9 is divisible by 3, so 243 is also divided by 3. It's a neat little trick. So 3 goes into it, what, 81? Notice I'm ignoring the negative. I'll take care of that later. 81, 3 goes into 81 how many times? I know it goes into 81 because 8 plus 1 is 9. It goes in 27 times. 3 goes into 27? 9. And then 9, of course, is 3 and 3. I'm looking for 5 factors, and I found 5. Don't forget him down here. He counts, too. So all along this little L shape is 5 factors of 3. So I'm going to pull out a 3. What kind of 3?
Negative.
I would pull out that negative 2, because a negative inside of the cube root is the same thing as a negative outside. I can prove it for you real quick. The cube root of negative 8 is equal to negative 2. And the cube root of 8 with a negative on the outside is also equal to negative 2. I could break it up into negative 1 and positive 8 and show you that way, but this kind of gets the idea across, that negatives in a cube root or a fifth root are going to pull through. What about a negative in a fourth root? It's got to be positive, so it would be undefined. You can't do a darn thing with it. So when I pull the 3 out, I'm going to take the negative with it. So I'm going to pull out negative 3. And then leave behind, back up. I got a step ahead of myself. Yes, I did. Pull out the negative 3. And then the variables. So erase that. 5 goes into 4 how many times? None. So none of the x's are coming down. 5 goes into 10 how many times?
2.
So we're going to pull out how many factors of y? 2. And then we're going to leave behind any numbers? No numbers, so x to the fourth. Anything else? No. And there's your answer.
Okay.
Yeah. I'm going to keep doing that. So the fifth index has to go in there. And there's your answer. Nice little answer.
Same method.
But it's the same method for each one. And that's the nice thing about it. You just have to worry about the index and how many you're going to group. So with square roots, you're looking for pairs. For cube roots, you're looking for 3 of them. For fifth root, you're looking for 5. All right. Next up in the little section here. I think out of all the sections in this chapter, this one's the easiest. I have to ask some silly questions now. See if you remember things. 4x minus 3 plus 5x plus 2y. Like I said, some silly things. Okay, let's talk about properties while we're here, since it's going to be on the final. What do I do? How? I have to kind of group them. So to group them, I need them change the order. So when I change the order of this thing, what property? Commutative. So the order then changes into 4x plus 5x minus 3 plus 2y. Okay? You remember that, right? When I get the 4x and the 5x next to each other under commutative, what's the next thing you do? Take out the common factor. What property? Distributive properties. So you would kick out the x. The minus 3 plus 2y is not going anywhere. What's left inside the parentheses? 4 plus 5. And 4 plus 5 is?
9.
And you get 9x minus 3 plus 2y. Can I do anything else to this expression? No, absolutely not.
Yes, just add
I'll kill you. Who did that the other day?
When?
Yeah.
No, I didn't.
No, it wasn't you. She did. Oh, she's good.
See there? Always trying to do something.
On you, yes, I know. Okay, so if I have something like 4 square roots of 2 minus square roots of 6 plus 7 square roots of 2 minus 3 square roots of 5. You know, some radical expression with a bunch of sums and differences. What am I looking for?
Like terms.
I'm kind of looking for like terms. So what are the kind of like terms here? The 4 square roots of 2 and the 7 square roots of 2. Why? Because I can factor out the square root of 2. So I'm going to use the commutative property. And I'm going to yank out the square root of 2 in the distributive property, and left behind is 4 plus 7 square roots of 2 minus the square root of 6 minus 3 square roots of 5. And then, of course, 4 plus 7 is 11. So you get 11 square roots of 2 minus the square root of 6 minus 3 square roots of 5. And that way you're using a property to simplify a radical with, kind of getting the idea that radicals behave like variables. That they have the same behavior as variables. And there's your simplified solution. Can I combine these two? No, they're different. This is like z and y. So don't even try to force them together. It doesn't turn into square root of 11 over here or anything silly like that. All right. So if they have like radicals, they are considered like variables in a way. So that's a lot of their beginning ones. That's boring. Oh, 36. Kind of boring, but it gets pointed across the point. Square root of 90 minus the square root of 10. Can I simplify that? Are they like terms? Yes, if you break it down. When you see a square root of 90, anything like a big number, try to break it down and see if it does something does come out and something gets left behind. You really have to do that with all radicals. 10's not going to work though. Why? It's just 2 times 5, and you're not going to get a pair. So the 90, what's the smallest number that goes into it? 2. And 45. Does 2 go into 45? No. So 3 and 15, which is 3 and 5. So my pair is 3. So I'm going to take out a 3. What gets left behind? 10. The 2 from the top and the 5 from the bottom. So you have to be looking at these things that are left behind. So we take out a 3, and we're going to leave behind the square root of 10. Is it a square root? Yeah. It's got an index of 2. It's got an index of 2. And then bring down minus square roots of 10. Well, what's 3 square roots of 10 minus 1 square roots of 10? 2 square roots of 10. By the distributive property. Take out the square root of 10, add the numbers that are left behind, and there you go. So it's pretty easy, right? Simplify the radical, combine any like terms, you're done. I don't think they get much harder than that. 38, which has a piece in it that I didn't see in the above ones, so let's just talk about here. 3, no, wrong one. 5 square root of 75 plus the square root of 48. Now, the only thing different here is when we simplify the radicals, we're not used to having a number sitting up front, so we have to be kind of cautious with that 5 and if there is another number out there. Okay, so 75, smallest number that goes into it? 3. Always start with 2. If 2 doesn't work your way up to 3. If 3 doesn't work your way up to 5. Because if 2 doesn't go into it, guess what else doesn't go into it? 4. It has to be even for 4 to go into it. So the only number the smallest number is 3. 3 times 25. And then 25 is obviously 5 and 5. So we're going to pull out a factor of 5. But when we pull out this factor of 5, it's going to run into this factor of 5. So there's a factor of 5 coming from the inside. There's a factor of 5 sitting on the outside. And when they run into each other, they create 25. They're going to multiply together. I've had people add them before. Kind of scary. So this becomes 5 times 5, which is 25. 1 factor from the inside, 1 factor from the outside. The square root of 3. Okay. So that's 5 square roots of 75. 48, smallest number that goes into it. 2. 24, which is 2, which is 2, which is 2. After you do a bunch of these, you start recognizing certain numbers keep showing up. 27 will show up a lot, 54 will show up a lot, 64 will show up a lot, 12s and 24s. So you start getting used to what these numbers are made up of. So what can I pull out? I can pull out this factor of 2. That it? I got a pair down here too. So when I put these two together, what am I pulling out? 4. The sign between these two is positive, so make sure you stay positive 4 square roots of this 3 that's left behind. Now, are they like terms? Yeah. So 25 square roots of 3 plus 4 square roots of 3 is? 29 square roots of 3. Because we can kick the square root of 3 away, add the two numbers together, and there's your answer. Not bad, right? Pretty easy for Friday. I can't get much harder than that for this section, which is nice for you. It's no fun for me. The hardest one I can see in the book is this one. 56. 56. 2y, the cube root of 27 x cubed. Oh, actually that one's not that bad. I'm gonna make up one. Make up. Gotta make it worse. The cube root of 128 x to the fourth, y to the fifth, minus 4 x y, the cube root of 16 x y squared. I hope it works. I was piecing together a problem in the book and a few extra things out of my head. So hopefully it works. All right. Start off the same way. Obviously they don't look the same now, but you don't know until you simplify them out. So let's start with 128. 2 goes into it. 2 goes into it. 2 goes into it. I think we did this one earlier. 2 goes into 16. 8. 2 goes into 8. 2 goes into 4. 2. It's a lot of writing, but it's not like it's hard. I mean, what would be hard is looking at 128 and going, oh my gosh, what's the perfect cube in it? I mean, that takes some time. This doesn't take much time at all. You just and write it out. Now we're going to group them in 3. So here's a triplet, and here's another triplet. So 2 triplets make 4. So we're going to pull out 4. Let's work with the variables next. 3 goes into 4. 1, so I'm going to get a single factor of x on the outside. 3 goes into 5. 1, so we're going to get a single factor of y on the outside. Okay. Left behind. A 2, an x, and a y squared. Hey, we're getting closer. This one has an xy squared, this one has an xy squared. But the numbers are different. This one's 2 and this one is 16. All right, let's simplify the second one then. 16 is a nice easy one to break apart. This is 2 and, which is 2 and, which is 2 and 2. Does it have a triplet? Yeah, 3 2s. So you take out one of the 2's from here, but it's going to run into that 4 up front. So when it runs into the 4, 4 times 2 of course is 8. So when I write it down, it's going to be -8, and then work with the variables. Can I pull out an x? No. Can I pull out the y? No, they're too low in factors. So it's going to be -8. Don't forget the x and y that are already out there. And then we have the cube root. Oops, I forgot something over here. Y'all made me forget it. Little 3. The cube root of our 2. And we didn't pull out the x and we didn't pull out the y squared. Now, are they like terms? Yeah.
You did it right.
That's amazing, isn't it? The hard part again is that number, so I stole the numbers from the book. So here we have 4xy, cube roots of 2xy squared minus 8xy, the cube roots of 2xy squared equals -4. Since these two pieces are exactly the same, you can factor it out, and what's left behind is just a 4 and a -8. Do you want me to do it? Factor them out? I mean, if you factor it out, you're going to be leaving behind stuff, and the common factor is xy, the cube root of 2xy squared. What's left behind? 4 minus 8. And if you distribute it back through, you're back to the beginning. But 4 minus 8 is -4 xy, the cube root of 2xy squared. The distributive property will save you when things get a little weird. That's a little weird. But it does help out. All right. So that's, what was that, 7-3, 7-4? What is it? 7-3. So let's start 7-4 while we're on a roll. 7-4 is the trickier part. And I have to be a little bit more patient of how I tackle it. So 7-4, multiplying radicals, or radicans, or irrational numbers. A lot of different ways of phrasing it. All right. So let's see here. If you have 4x squared y times negative 3xy cubed, how do you multiply these two together? Properties. What do you have to get next to each other? The numbers, the x's, and the y's. You have to group like things next to each other, unlike like terms. Like terms are totally different because they're added and subtracted. So here we're just trying to get the numbers next to the numbers, the variables next to the variables. What property allows you to move them all around? Commutative property, flipping them around. So I'm going to get the 4 and the negative 3 next to each other. So it's going to be 4 times negative 3. I'm not going to, this is the mental step, but I want to show all the little pieces. We've done this before. Then we're going to get the x squared and the x together. So x and x squared. And then we're going to get y and y cubed next to each other. So it's a mixture of commutative property and associative. I'm associating the numbers, the letters, the x's and the y's. All right, and then 4 times negative 3 is negative 12. X times x squared, x to the third. And y times y cubed is y to the fourth. And there's your answer. There is no distributive property going on there because there's no addition and there's no subtraction. Radicals are going to behave the same way. Same idea that radicals behave like variables in some sense. So if I have, for example, 3 square roots of 6 times negative 2 square roots of 8. 3 square roots of 6 times negative 2 square roots of 8. We're going to be using the forward property. The square root of a times the square root of b is equal to the square root of ab. So anytime you have two radicals multiplied together, you're going to put it under one radical and just multiply the stuff together. Of course, anything sitting on the outside stays on the outside. So when we do the same kind of process, we're going to group the negative 2 times 3, and we're going to group the square root of 6 times the square root of 8. Again, this is the mental step. This is the one that usually gets done in your head, but I'm just writing it down to show you all the little pieces. Negative 2 times 3, of course, is negative 6. And then using this property up here, what's the square root of 6 times the square root of 8? Which is 48. So we get negative 6 times the square root of 48. Yay! Am I done?
Yes.
I need to break it down. You can't leave big, nice, even numbers underneath the radical. So when they get bigger than 10, I highly suggest you start breaking them down and seeing if you can simplify it. Because if you leave it like this, you lose 2 points. Not just 1 for not simplifying, 2 because you really need to simplify. 2 out of 5. That's a big chunk. So 2 goes into 48 how many times? You're all still whining back there. So 2 goes into 48 how many times? 24. 2 goes into 24 how many times? And then 2 and then 2 and. So obviously it does break down. That's a lot of 2's. So how many pairs do I have? 2. So here's 1 pair of 2, here's 2 pair of 2. So what's coming out? It's 4. And then that 4 is going to run into negative 6. 4 times negative 6? Negative 24. Square roots of what's up behind? 3. So 3 square roots of 6 times negative 2 square roots of 8 is the same thing as negative 24 square roots of 3. Cool. Good think about that. All right. What else? Oh, we've got to cover this one. Square root of 3. Square root of 3 times 2 square roots of 6 minus 4 square roots of 2. Square root of 3 times 2 square roots of 6 minus 4 square roots of 2.
Oh my god.
It's not that bad. What property?
Distributive.
Distributive. So when you distribute, you're going to go square root of 3 times 2 square roots of 6. When you're multiplying this, you're going to think you're distributing inside of the multiplication, but you're not. You're going to multiply number to number and radical to radical. It's not the distributive property. It is actually the commutative property and associative. So when I distribute this and I go square root of 3 times 2 square roots of 6, that's going to equal 2 square roots of 18. So you get 2 square roots of 18. And then when you distribute square root of 3 to negative 4 square roots of 2, literally what's happening is you're going 1 times negative 4 is negative 4. And square root of 3 times square root of 2 is square root of 6. You can see where people start thinking it's a distributive property because you're going 1 times 4 and square root of 3 times square root of 2. You're kind of looping, but you're really not. You're grouping. All right, is that my final answer?
No.
Heck no.
Gotta simplify.
18, if you can think of it real quick, what it is, that's great. If you can't, 2 goes into it 9 times, and 9 is, so I can pull out a, but don't forget he runs into
2.
that 2. So we're going to get 6 square roots of, this guy's left behind, he kind of gets stuck up there, but he's there, 2, minus, can I break 6 down? I can break it down, but it's 2 and 3, that doesn't go anywhere. So minus 4 square roots of 6. Can I combine these? No. One's got a square root of 2, the other one has a square root of 6. That's like x and y. Don't combine them. All right. If you can do this, then we can do more. No, I'm not going to do it today. And